Students, welcome to next class of reaction mechanism of octahedral complexes. In the last class we had learned regarding the inert and labile complexes. Okay, so this is summary, we will do it now. Okay, according to valence bond theory we had learned regarding the inert and labile complexes depending on the vacant orbital sites. Okay, so 3 and nd and s orbital and p orbital, np orbital, is it right? So this is how we had learned. This is d orbitals 5 and ns orbital 1 and np orbitals like this. And we have seen that 1 2 3 4 5 6, so these orbitals is been occupied by the ligands, and you can see here, so these are vacant orbitals. Okay, so in the slow reaction rate inert, slow reaction inert, so this under this category we can see slow reaction and inert. So d3, yesterday's class I said, so d3, if I go for these 3 electrons, what will happen? There is no vacant orbitals because these are being occupied by the ligands, and that's why this will be inert, slow reaction and inert reaction. Similarly, low spin d4 system, see, low spin d4 system means what? 1 2 3 4. So here also there is no vacant orbitals. d5 1 2 3 4 5, no vacant orbitals. d6 1 2 3 4 5 6, no vacant orbitals, and that's why the reaction is slow and we call it as inert. The reaction is slow and inert. An exception case is what? d8 system yesterday's. Okay, why the VBT fails here? Because it's in the strong field d8, so system is a square planar system and it is, the reaction is slow and inert. But according to VBT, so this reaction, this D8 systems will be labile, but here it is inert, and this exception case. This is why the VBT fails here, and that's why the CFT comes into existence in the next theories. Similarly, now you can see one case here, moderate rate, so not fast, not slow. So that will be weak field D8 systems here. Strong field D8 system will be very slow. Weak field D8 system, so if you go for weak ligand here, for the nickel D8 system here, so you can see it's a moderate rate. So D8 system is exception here, so neither it will be fast neither it will be fast, it will be moderate or it will be slow reaction, D8 system. And now we will go for fast reaction. Yes, absolutely. So for the fast reaction, D1 system, because if I put the electron here, 2 vacant orbitals will be there, fast, very good. D2 system, 2 electrons, 1 vacant orbital, fast. High spin d4 d5 d6, see, high spin is there, so high spin definitely. So d4 means what? 1 2 3, so I will put here 4, so 1 vacant orbital will be there. Then d5 1 2 3 4 5, okay, so high spin. So d5 d6 d7 d9 and d10, so this will be fast reactions. Okay, so because of the vacancy there, so because of the vacancy created here, so because of this you can see that the fast reaction, these d1 d2 and the high spin reaction of d4 d5 d6 d7 d9 and d10. Okay, so this will be fast reactions, and labile, we can say they are labile. So this is how you should know the all the DN configurations with respect to the labile as well as labile as well as labile as well as what you say inert complexes. Okay, so these all have EG orbitals, so d4 d5 d6 in field EG orbitals, and asymmetrically filled, and that's why they are very fast. Okay, they are very fast reactions here. Okay, so this is how the inert and labile complexes general summary today we have completed here, pertaining to the last classes, continuation to the last classes. Now next concept is substance substitution reaction in octahedral complexes, that is what aqueous medium. So when I go for substitution of this octahedral complex with a new ligand here in the presence of water, we call it aquation. So this reaction is called as aquation or acid hydrolysis here. So what will happen? So this will compete, this water molecule will compete, and it is going to insert here like this Ma5 H2O. So n plus 1, so plus n, so 1 is going inside here ligand, plus X minus. So X is going out and water is substituting here inside this complex. So it's called aquation. Okay, water, not this new ligand. So new ligand is still silent. So water is going to compete here. That's why aquation or acid hydrolysis. And thereafter this will be replaced by the new ligands like this, and water is going out. Okay. So such reactions where water is replacing the internal ligand from the complex, we call that reaction as a aquation reaction or acid hydrolysis. Similarly, if OH of the water replaces, then we call it as a base hydrolysis here. Okay, now see here, same complex I am taking here, Ma5X here, Ma5X. Now in base of water I am taking here. Okay, so base of water OH minus of the water, so you can see here Ma5OH plus X. So OH is replacing this internal X here outside, and that's why such reactions we call as base hydrolysis. Further, if I treat this with new ligand Y minus, so OH minus will be out and Y will go inside. So like this. Such reaction we call as a base hydrolysis. Now coming to this acid hydrolysis of octahedral complexes through mechanism. So in the last class we had learned regarding the SN1, SN2 mechanism. So SN1 mechanism is dissociative, you know from the last class. Now you see here, so we'll go from that mechanism. So Ma5, this is a complex octahedral. Slow reaction will be dissociation. So what I will get now, 5 coordinated intermediate Ma5 here, okay, n plus 1, and slow plus x minus is going out. This is the first step. And second step, what will happen now? So this 5 coordinate intermediate will react with the water molecule. Fast reaction, I get this complex C, okay. And the rate of reaction depends on what now? Only this concentration of the reactant, okay. That's why unimolecular. That's why this is a process of unimolecular reaction, SN1 reaction of the equation, okay, or hydrolysis, acid hydrolysis. Now similarly you can see SN2. SN2 means what? This association. Association means what? We are going to get 6 coordinated. Now see here, Ml5UXN plus H2O, slow reaction. So you get 6 coordinated reaction here. So 5, 6, 7 coordinated intermediate. Now the reaction is fast here, and what will happen now? So one of the one of this ligand is going to be substituted by the going outside, and we are going to get this complexes. Now the rate depends on what? The concentration of this reactant as well as the water molecule. That's why it is called as bimolecular reaction, SN2 mechanism. So this is how the acid hydrolysis proceeds with respect to the SN1 and SN2 mechanisms, okay. Now what are the factors affecting the equation now? So this is what 2 factors we will learn today, and remaining 2 factors and the remaining factors we will see in the next slides, followed by the base hydrolysis mechanism. Now here, so factors of the equation. So this whatever SN1, SN2 rate of equation what we learned, so we'll see how they are going to affected by the some factors. For example, change of charge of the substrate, CHARG, charge of the substrate. See here, positive charge, that is main. If on the complexes, if the positive charge increase in the positive charge, so what will happen now? Increase in the positive charge will decrease the rate of equation. This point you should remember, okay. Increase in the charge positive on the complex will decrease the rate of equation. See one example I have taken here, cis cobalt diethylene bis ethylene diamine dichloro cobalt plus complex. So you can see here is 100 times faster than the plus 2 complex here. Cis same CON twice plus H2O plus 2 complex. So this is how we can give the reaction, cis ethylene diamine bis dichloro plus water. When the reaction is very fast, and get this water into here. So COEN to H2O plus here. So water is been introduced here, and from positive plus charge I am going to get here plus 2 charge. Now the reaction is very fast. This reaction is very fast here. So from plus charge, if I want to go from plus 2, the reaction is far. Further, if I take this plus 2 and go for equation here, the reaction is slow. That's why it is 100 times slower. As the positive charge, see now what I get now here. So when I go for plus 2 charge is converted to plus 3 charge plus Cl minus is out here. So 2 molecule, this is going to inside the clone, Cl minus is going out here, and I get here now plus 3 charge. See, so this again is slow, again slower than the plus 4 charge, like this. So as the positive charge increases, what will happen? The rate of equation goes on decreasing. So first one is very fast, then slow, then again slow, then like this. Is it right? The rate of equation decreases and decreases. So that's why as the positive charge on the complex increases, the rate of equation becomes slow and slower. So this is the first factor of the equation which will help you for the competitive examinations. Second is what? Now you can see strength of MX bond. See, metal to leaving group bond. So metal is there and the leaving group bonds here. So this is what Ma5 what we give now here. So Ma5, so Ma5, this is the leaving group, okay. This is the leaving group. How should be that strength? So now see, I have taken some leaving group here, CF3CO minus, CCl3 trichloro ethane CaCO minus, okay, in the form of acidic group is there, CH3, and so this is the electron withdrawing group is there for this CO minus, and the electron donating CH3 CH2CO minus, okay. So acidic group we get. So here you can see the electron withdrawing here, F is strong electron withdrawing chlorine, and followed by the electron donating, that is CH3 CH2 alkyl group. So this is a dissociation constant. So you can see here dissociation minus 14 minus 14 minus 10. So dissociation constant is less for this because of electron donating group here. But here you can see that for this acid you can see that electron donating group is electron withdrawing group is there here. So that's why dissociation also you can see here it is a little bit less for fluorine, strongest electron withdrawing group, and 5 for this one chlorine. So finally you can see rate of equation here. So a rate of equation also you can see here it is very least here. See, so it is fast in fluorine, strong electron withdrawing group, very fast equation, then followed by next and last one you can see here the electron donating group, that is zero point 0.3. So how does this, we can see that mx bond. So you see here dissociation constant, you see. Okay, so what does the dissociation, higher the dissociation constant shows what? So here higher the dissociation constant is what? So this one, is it right, last one? That means what, mx bond is how it is very strong. Okay, so this group this group CH3CH2 is not going to be released from this metal. So whatever metal is here, so this group is not going to be leaving easily. Why? Because of the electron donating nature, and that's why dissociation constant is very high. When dissociation constant is high, then how will be the rate of equation? It is low. Why? Because water cannot enter into this. Similarly, you can see here the dissociation constant is least here. Why? Fluorine is a very good electron withdrawing group, so dissociation is very low here. And so what happens for mx bond? It is weak. So when dissociation is low means what? It is very weak. So when mx bond is weak, this can be leaving group can be easily gone out. So this can be taken by H2O. So that's why rate of equation is highest here. So similarly, basicity, you see one more parameter I can add. So rate of equation decreases with increase in the basicity. So here basicity is more. So rate of equation decreases with increase in the basicity of the leaving group. So like this. So this is how the factors affects for the rate of equation. So here too I have taken. In the next slide I will go for the another factors followed by the base hydrolysis. Hope you understood this class. Thank you.